All right, so let's get started. So today we're going to be doing more on interior point methods. There's a little bit of review from last time. So if you remember last time we finished off support vector machines. We talked about duality for support vector machines. So we have the primal dual pair here of support vector machine problems. The primal is to maximize the margin by minimizing the squared norm of the weight vector plus some constant times the number of times the slacks, subject to this is feasibility, right? So this is saying that everything is correctly classified except possibly for the slack. And then the dual is a minimization problem with box-constrained variables, which we think of as weights on the examples. So K here is the Gram matrix, the matrix of pairwise dot products between the examples. And if you remember, the Gram matrix lets us totally avoid reasoning about the examples themselves once we have the dot products. And so that's great, right? It lets you solve kernelized SVMs very quickly, even in very high or even infinite dimensional spaces. We talked about interpretation of the support vector machine dual. So support vectors, complementarity, allowing us to, we could use the complementarity conditions to help us reconstruct the primal from the dual, right? So we get the V directly from the alpha. Its V is basically A transpose times alpha. But to get the intercept, the classification boundary, we had to use complementary slackness. All right? So you guys should all be familiar with pictures like this. Probably tired of them, especially if people draw nice margins there. That's maybe there. Make the margins actually go through the support vectors. All right, so we talked about the kernel trick, which is how to do high-dimensional feature spaces fast. It works for any positive definite function, which is k of ui comma uj, right? So the idea there was that ui is some feature function, sorry, other way around. Some feature function applied to ui is xi, and so to get the dot product between xi and xj, rather than building the infinite dimensional xi and xj, we'll just apply the kernel function to the finite dimensional directly observed data points. You can use any positive definite function k. People have gone and proved a bunch of useful functions to be positive definite. We gave the examples of polynomials, homogeneous polynomials, the linear kernel, of course, and Gaussian radial basis functions. So here's the very colorful picture of a Gaussian radial basis function, and it can let you have basically any smooth decision function, and then the level set of that decision function would be your decision surface. Okay? So questions on support vector machines? Yeah?
If I have a kernel function that's flexible, will it not overfit?
Right, so you do have to worry about overfitting and kernel. So often people will advise you to use a restricted function class to avoid overfitting. What kernels do instead is they use large margins to avoid overfitting. So you can think of that as being similar, that there's not that many functions that could separate your data with a very wide margin. And so that's the complexity control in support vector machines. And yes, you do need complexity control to avoid overfitting. Yeah?
It's probably a related point worth mentioning if you go back to your slide. Did you put a C there?
Yes.
Was it a C times?
C times 1 minus, right, you have to penalize the slacks.
Yeah, so I mean that answers the question. Because controlling C is going to control the amount of overfitting. Right, if I make C, for example, I can't do it big or small.
Right, so C is the penalty on the slacks, so big penalties on the slacks mean not very complicated functions.
Yeah.
Right, so if you make C large enough, it's going to pick V equals 0. Right, and that's the ultimate in complexity control. You're not going to overfit if you don't fit. And if you make C very small with a very flexible kernel, and if you have noisy data especially, you'll overfit. Okay. All right. A little bit more review. We talked about the linear feasibility problem at the end of class. So that's ax plus b bigger than 0 for some matrix A, which we'll say is, I'll draw it here, right? So A is m by n, right? And so we have an n vector x, right? And then we have then an m vector b. I don't have a space to draw it here, but we'll maybe fit it in there, right? So this is b, and it's an m vector. So we talked about trying to make a summary of the feasible region. The first idea was to look for the ball center of the feasible region, but because of examples like this one, the ball center could be a bad summary, right? So you could either have a very long skinny triangle or the triangle with its tip chopped off, and they're very different feasible regions, but they have the same ball center. So the ball center can't be a very good summary. And then we talked about finding the max volume inscribed ellipsoid, which is a much better way of summarizing a feasible region. You can actually prove that it contains 1 over n of the volume in n dimensions, but it's kind of expensive to find it. And then we talked about what we're going to be talking about today, how to get maybe some of the volumes of some of the benefits of the max volume ellipsoid without having to pay the price for having to find it. All right? And the way we started on that was to define an analytic center of the linear feasibility problem. So the analytic center was the point x that maximizes the product of the distance from x to each of these constraints, right? So the individual constraints are ai transpose x plus bi greater than or equal to 0, right? So ai is the ith row of A, right? This is ai, right? And ai transpose x should be bigger than or equal to bi, or plus bi should be bigger than or equal to 0. And the distance to a constraint would be then ai dot x plus bi whole quantity divided by the norm of ai, right? Because if we move x around, if ai is unit norm, then the fastest we can make this change is by moving x parallel to a in the same direction as a or minus a. And then what that will tell you is that it moves exactly, this slack moves at exactly the same rate as x does if a has unit norm, right? And so maximizing the product of the distances to the constraint, well, you take the product of this, you can rewrite it by taking the log, right? And then these minus log of the norm of AIs, those don't depend on x, and so we can just discard them. And so we can minimize minus the sum of the logs of the slacks, right? And that finds us the point which maximizes the product of the distances to the constraints. And you can think of that as sort of a soft version of the ball center, right? The ball center maximizes the minimum distance. Here we're maximizing the product of distances, which if one of the distances is very small, it'll make the whole product small, right? So it's like a soft version of the minimum. All right? So analytic centering problem makes sense? Okay. So the analytic center itself isn't necessarily a great summary of the feasible region, but in a few minutes from now, we'll define the Daikin ellipsoid. And the Daikin ellipsoid centered at the analytic center is going to be a pretty good summary of the feasible region. In fact, we're going to be able to prove that it contains 1 over m of the volume of the feasible region, where m is the number of constraints, which is not as bad, not as good as 1 over n, right? So m here is bigger than n, but it's much cheaper to find. Okay? Yes? Why? So the question is, why do we choose to maximize the product instead of the sum of the distances? We could try that. We'd have to go prove another whole pile of theory similar to what I'm going to prove later in the lecture. My guess is that not all of it would go through, but it seems like a perfectly reasonable idea. So might be an interesting thing to try. Yeah.
Maybe because of what you said, if you maximize the product, you're actually pushing all of them. You're pushing the smallest one.
Right, right. So maximizing the product, you could be maximizing the sum of distances. Like if you're between two parallel constraints, it doesn't determine it, right? You can move back and forth while keeping the sum of distances the same. And so it doesn't, like every point in the box, in a box would maximize that. It's a very good point. Yeah?
Also, that this doesn't allow you to leave the feasibility, right? If you do a minus infinite,
Yep.
energy gets to
Right. I guess I was imagining maximizing the sum subject to not leaving the feasible region. But yes, right. It's nice to think that you're sort of, getting pushed away from the constraint harder and harder as you get closer and closer to it. Right. So yeah, could be another whole interesting pile of theory with maximizing the sum, but we're going to go with the product for the rest of the lecture. All right, so the Daikin ellipsoid at the analytic center is going to be contained inside the feasible region, and it's going to contain at least 1 over m of the volume, and it's going to be cheaper to find than the ellipsoid center, and so we're going to go with that as our summary of the feasible region. Okay? All right, so one way to think about the analytic center is to pretend that there's some kind of force that's at each constraint pushing a particle away from that constraint. And so, if you put your particle here, then you'll have a big normal force from this constraint and a big normal force from that constraint. And then from this constraint, there'll be a smaller normal force. From this constraint, there'll be maybe almost none, right? And then from this one, same thing, right? And so you can see this particle wants to move, right? Because it's got a big forces pushing it that way. And so if, on the other hand, you go, let's say, about here, right, then the closest constraint's going to be that one. This one's almost as close, right? This one's just a little bit farther, so maybe like that. There's a pretty small force there and a pretty small force that way, right? And so this one looks much closer to imbalance, right? I only sketched it, but this is approximately where the analytic center is. Okay? So you can think of this as some kind of physical system, although I don't actually know of a force that has 1 over distance as its strength when you're going from an infinite plane of source of whatever that force is. But, whatever. It at least sort of gets our physical intuition. All right, so one way to find the analytic center is Newton's method. We did this very briefly at the end of class on Tuesday, but I want to do it in actually a little bit more detail. So if we have f, this is the, we call this the log barrier function. It's the thing that we're trying to optimize to get the analytic center. If we take its first derivative, we get derivative of log is 1 over. So we get minus 1 over ai transpose x plus bi, right? And then by the chain rule, we multiply by this whole thing by the gradient with respect to x, which is ai, right? And so, and then we're going to sum that over all I, right? And so if you look at this, this is a bunch of vectors, each of which is getting multiplied by a scalar, summed and added together, right? So if we define SI equals AI transpose X plus BI, right? And if we define YI equals 1 over SI, right? Then here, this is this here is YI, right? And so what we're getting is that minus A transpose y is the gradient, right? And so the first order condition is that that has to equal 0. Okay? So this is the first order condition. Let's take the Hessian now, right? So we're going to get still a sum over I and a negative sign. And then the derivative of 1 over something is minus 1 over the same thing squared. So that's AI transpose x plus BI to the minus 2. And then we have an AI from before, and the chain rule gives us another AI, so we get AI transpose, right? And so using this same notation, we can write that as the Hessian is equal to A transpose. So I'll write capital S to be the matrix which has little s on the diagonal. So this is s to the minus 2a. It's also equal to A transpose y to the positive 2a because y is 1 over s. Okay? So Newton's method, we take the Hessian, multiply its inverse by the negative gradient, and so the Newton direction is delta x equals A transpose s to the minus 2a inverse A transpose y. Right? So if we want to do Newton's method, we just calculate the slacks, do 1 over the slacks, and then calculate the Hessian inverted or solve the linear system, and that gets us our Newton direction. Let's make that clearer that that's a delta and not an A. Right? So this is kind of, that's kind of a nice algorithm. It's pretty simple to write down. And a couple of things we can say about it. So this is a strictly convex function, which means that the Hessian is going to be strictly positive definite, which means that the Newton direction is going to be a descent direction. And so that means that Newton with line search is going to converge from any feasible initial point, or any strictly feasible initial point, because if you're on the boundary, one of the logs will be infinite. Okay? And in fact, it's going to converge quite quickly. We'll see that later. The other thing that you might notice is that I said from any feasible initial point. And so that means that we need to know something that's in our feasible region to start with. There are ways to get around that as well, and we'll see those on some later slides. Okay? So everybody understand this algorithm? All right. So let's try and understand a little bit about the behavior of this algorithm. So what I'm going to do is define the Daikin ellipsoid, and then we'll show a connection between the analytic center, the Daikin ellipsoid, and the feasible region. Okay? So I'm going to write E of x0 for the Daikin ellipsoid centered at x0 to be all x such that x minus x0 transpose h x minus x0 is less than or equal to 1, right? Where h here is the Hessian of the log barrier function at x0, right? So it's what we calculated on the previous slide for Newton's method. So another way of saying this is that the Daikin ellipsoid is the unit ball of the Hessian norm at x0, right? Where if you remember the Hessian norm of x was defined to be the square root of x transpose hx. Okay. So I drew an example here, or rather I had MATLAB draw an example for me. And you can see that the Daikin ellipsoid at the analytic center does in fact contain a pretty good fraction of the feasible region here. Probably more, there are 7 constraints here, and it looks like it contains more than 1/7 of the volume. But that's just a bound. Okay? So we can prove 2 things about the Daikin ellipsoid. One is that for any strictly feasible point x0, if we calculate the Daikin ellipsoid centered at that point, that's going to be contained in the feasible region. And so that's kind of a nice thing, because it means that Daikin ellipsoids, they don't let us just summarize the geometry of the feasible region. They let us summarize the geometry of the feasible region near any particular point, right? And so I've seen that used to good effect in some optimization algorithms where you calculate the Daikin ellipsoid somewhere and use it to figure out, for example, how to sample the feasible region. Okay. You can define a Daikin ellipsoid. So here I just did it for inequality constraints. The analog for equality constraints is it's exactly the same thing. You take the Hessian of the log barrier of the inequality constraints, but then you just intersect it with the affine constraints. So you take a slice of through the middle of the ellipsoid, which is still an ellipsoid in smaller dimensions, and that's the analog of the Daikin ellipsoid if you have equality constraints. Right? And then the other thing that makes it really useful is if you take the ellipsoid that's centered at the analytic center, and you take it and you grow it by a factor of m around its center, then it's going to actually contain the feasible region. Right? So that's nice, right? It means that the ellipsoid doesn't just tell us an inscribed ellipsoid, it tells us a circumscribed ellipsoid. So we have both inner and outer bounds on the feasible region from the same calculation. Okay? And the fact that you have to scale it by only a factor of m means that the original Daikin ellipsoid must have at least 1 over m of the volume of the feasible region. Okay? So that's kind of, to me, very surprising and cool. So let's go ahead and prove it. The other thing that's surprising and cool is that the proofs are actually quite simple. So here's the, this is the Daikin ellipsoid centered at x0, right, where h is the Hessian, s is the slack vector, you put it on the diagonal, right, s is ax0 plus b. So this is for any feasible point x0, not just the analytic center. So how do we write this constraint, right? So if you remember, if we just remember the expression for the Hessian, right? One way of saying the Hessian was the sum over I of si to the minus 2 times ai transpose, right? That was, and so if we just write this out like that, right, this is the same as saying that sum over I of ai transpose x minus x0 over si, whole quantity norm squared is less than or equal to 1, right? And so, oh, you're right. No need for the norm. It's a scalar. It's true with the norm, but let's not write the unnecessary norm. So this is true, right? Because we just took the Hessian and factored it, right, into two pieces, took one of the 1 over s's and put it with each piece. So that sum being less than 1 means that, well, every term in the sum has to be less than or equal to 1. And with this, getting rid of the square, that's the same as saying minus 1 is less than or equal to ai transpose x minus x0 over si is less than or equal to plus 1. Right? So let's take this left-hand one and multiply through by s, right? So we have minus si is less than or equal to ai transpose x minus x0, right? And now we had before the definition of right, si was equal to ai transpose x0 plus bi, right? That was just the definition of si. And so we can just take the ai transpose x0, substitute for it using this equation, and we'll get that we get rid of the s and put a bi in its place, right? So we'll get 0 is less than or equal to ai transpose x plus bi. Okay? So very, very simple proof right? And this shows that X is feasible because it satisfies the inequality constraints for all I. So, so very, very simple proof that the Daikin ellipsoid is contained in there, in the feasible region. That's kind of nice. So the proof the other way is slightly harder, but not much. So what I'm going to prove now is that if you take the Daikin ellipsoid not at an arbitrary point, but at the analytic center, right? So I'll just scratch that out, and expand it by a factor of m, it actually contains the entire feasible region. Okay? Expanding the radius by a factor of m. Okay? So, yeah, that's a good question. Well, let's prove what I have here, and I'll think about whether that's actually what I wanted to prove. And so okay, how are we going to prove this?
It has to be the volume, because otherwise the proof that you can get the volume of the ellipsoid should be at least 1 by m of the volume of the...
Right, that wouldn't hold. And so what I was worrying about was whether that's equivalent to this statement here, right? So let's show our assumptions here. So we're going to assume that we have some arbitrary feasible point, x, and we have the analytic center, xac, and here's the first order condition for it being the analytic center, right? If you take 1 over the slacks at the analytic center, call that y, then A transpose y has to equal 0, right? And then we can define the Hessian at the analytic center, which is A transpose y squared A, right? And so then the Daikin ellipsoid would be x minus xac transpose h, x minus xac less than or equal to 1, right? And so this looks like I'm expanding it by a factor of m along every dimension, right? So I didn't notice that. That's a very good point. This is still, it's almost the same proof as what's in Boyd and Vandenberg, so I'm going to have to go back and see what I'm missing. But let's look at the proof anyway, because it's kind of interesting. Right, and what I'm actually going to prove is that it's less than m squared plus m, which makes very little difference, but the proof that it's actually less than m squared is somewhat longer, and so I didn't want to do that one. Okay, so this, I'm just going to rewrite this term here, right? Same way I did before, sum over I of yi squared ai transpose x minus xac quantity squared, right? And what we want to do then is show that that's less than or equal to m squared plus m. And so we're going to do the same trick as before, right? We know that yi is equal to 1 over ai transpose xac plus bi, right? And so I'm just going to substitute that for ai transpose xac here, right? So this is equal to the sum over I, yi squared, ai transpose x, and then minus, so 1 over yi is ai transpose xac plus bi. So we'll get AI transpose XAC is yi 1 over yi minus bi, right? So it's plus bi minus 1 over yi, right, squared. Now we can consider this as a sum of two terms and write out the square, right? So this is equal to the sum over I of yi squared. Now we have AI transpose x plus bi squared plus 1 over yi squared minus 2 AI transpose x plus bi over yi, right? And now, oh, and this whole thing is, it was squared, but we wrote out the square, so we get rid of that. And now we're going to do a couple of things. First, we have yi squared times 1 over yi squared. That's 1. There are m terms in the sum, so that's going to give us an m, right? So that gets rid of that term. Second, this term, 1 over yi is positive. AI transpose x plus bi is positive because x was assumed to be feasible. So this whole term is positive, then we're subtracting it, right? So we can make the whole thing bigger by just dropping it. So we'll put less than or equal to m, and we've taken care of this term. And then plus sum of yi squared, AI transpose x plus bi squared, right? And now this is a sum of squares, right? And because all of the terms in the square are positive, the square of the sum is going to be bigger than the sum of the squares, right? So this is less than or equal to m plus sum over I, yi, AI transpose x plus bi, and then the whole thing squared, right? And then what do I want to do here? I want to change this x into an XAC, right? Because if I could do that, then this whole thing would cancel, right? This would be another whole bunch of ones. And the reason I can do that is that what is the reason I can do that? It's got to have something to do with this condition here. Yeah. All right, well, we'll just write that this is question mark less than or equal to m plus m squared, because clearly this proof is having more problems than I anticipated when I wrote it down. So let's consider that an IOU for a better proof later. And change the slide before anybody notices that I didn't finish the proof. All right, so modulo a couple of missing steps, we have the containment, and so what does that tell us? It tells us that there's two very different ways to find a feasible point of your set of linear inequalities. One is what we talked about a bunch of lectures ago. We find a feasible basis, which is a combinatorial search, right? And the other is to find an analytic center, what we just talked about, by minimizing a smooth function, right? And in fact, it's a really smooth function. It's infinitely differentiable everywhere inside the feasible region. And the fact that you can do this, that you can check feasibility of a set of linear inequalities or find a feasible point using either an analysis style method or a combinatoric style method. That's what I was talking about when I first introduced the interior point algorithms, right? It basically tells you that, that linear programs, linear feasibility is sitting sort of halfway between the analysis world and the combinatorics world. Okay? So does that make sense? Yeah. Right. It certainly is going to. So the volume of the ellipsoid is going to be related to the product of the distances, but it's not exactly the same because you have, these distances, they form this diagonal matrix, but then you multiply it by A transpose and A on either side, right? And so it's not clear to me that it is maximizing it, but it is at least approximately maximizing it. That's a great question. Yeah.
So can you imagine a scenario where you have sort of one constraint on one side and lots and lots of constraints on the other side?
Right. It'll push it. Right. And that's exactly why you get only the 1 over m instead of the 1 over n. Right. So the other thing that you can do is if you take every constraint and replicate it, you'll be pushing twice as hard away from each of the constraints, and so it's going to shrink the Daikin ellipsoid. Right? And so you can sort of make things as bad as you want by adding more and more constraints, but that doesn't violate the theorem because you're making m really big at the same time.
So that makes it seem like you wouldn't actually be finding the maximum volume ellipsoid. You wouldn't put the
No. So the Daikin ellipsoid is not the same as the maximum volume ellipsoid. The question before was whether the analytic center is the spot that has the largest volume Daikin ellipsoid, which seems plausible, but I can't prove it off the top of my head. Yeah. A bunch of great questions. All right. So I pointed this out briefly at the end of last class, but one of the nice things about the analytic center and the Daikin ellipsoid is that it relieves bad conditioning, right? So if you remember the example of a sort of very skinny triangular feasible region, if you find the Daikin ellipsoid at the analytic center, it looks like that, right? So it's actually still taking up a pretty big volume of the feasible region. And you can imagine making an affine transform of the feasible region to take the analytic center to the origin, let's say, and make the Daikin ellipsoid be a sphere. Right? And the nice thing is that actually works. The analytic center and the Daikin ellipsoid are invariant to affine transformations, taking x to w, where w is mx plus q for some invertible m, right? So m inverse exists, and some shift q. Okay? And so the feasible region after that transform is capital W, which is all of the w's such that the x that you would get is feasible, right? So solving for x in terms of w, right, is m inverse times w minus q, right? You just move the q over and multiply by m inverse. And so this says that ax plus b is bigger than or equal to 0 for the x that corresponds to this w, right? So that's what I mean by the affine transformation of the feasible region. And the claim is that the analytic center, right, W sub AC, is equal to M X sub AC plus Q, right? So it transforms the way that you would expect. And what happens to the Hessian? Well, you have H sub W is equal to M inverse transpose H sub X M inverse. Right? And so, in particular, if we suppose that h sub x factors, let's say the Koleski factorization, right? So that would be r transpose times r for a lower triangular r. And then if we take m to be equal to r inverse, right? So m equals r inverse, then we have hw equals r inverse, sorry, m is equal to just r, right? So that we get r inverse transpose, r transpose r, r inverse, right? And that's equal to the identity. All right? So we can always take the Daikin ellipsoid to be to a sphere and the analytic center to the origin by an appropriate affine transformation. And that's kind of nice, right? You sort of expect it because we know that an affine transformation isn't going to change where the optimum of a convex function lies. And we also know that Newton is affine invariant, so the Hessian should transform the way that we expect from Newton. Okay? So basically, Daikin ellipsoids are the cure for your conditioning problems. Sounds like a shampoo ad, but... I'm sorry, a special name for what? Oh, yeah. The name for this transformation is an affine scaling, or an affine scaling. I mean, I guess all of these are affine scalings, but if somebody tells you they're using an affine scaling algorithm, they mean one which transforms the Daikin ellipsoid to be a sphere. There may be other names, but I don't know them. All right. Now is probably a pretty good place for a break. So let's take a brief break, and we'll come back. All right. So let's get back started again. So the first thing is that I was careless in how I read Boyd and Vandenberg, and apparently a whole bunch of other papers. They say only that if you expand the ellipsoid by a factor of m, the radius, that it covers it. They say something which, if you read it in anything except the most careful way, says the volume, but that's not in fact what they're saying. So in fact, the volume is the radius expands by a factor of m, which means the volume is m to the n, right, difference, which seems like a lot. But if you think about it, it's actually not so bad algorithmically, because what you're often concerned with is the log of the volume, which then is just n log m, which is still polynomial in dimension. For example, if you're trying to find something by cutting an ellipsoid in half repeatedly, right, then the number of times you have to cut it in half is going to be proportional to m log n, right, or n log m. So the Daikin ellipsoid is still a pretty good summary, but the volume factor was exponentially off from what I was saying it was, so I apologize for that. The other thing is, so that's that. Okay, so now let's move on to linear programs, right? So we did linear feasibility, and that got us the analytic center and the Daikin ellipsoid. For a linear program, instead of just finding x, we want to minimize C transpose x for some linear function. And we can actually do pretty much the same trick to a linear program. So here we just add together the objective and some multiple of the barrier, right? And so we have some centering force that we want and some optimization force that we want to follow. And we just have a parameter t which trades between the strength of the two forces, right? And the central path is defined as x of t for all t greater than 0, right? Just the set of things you can get by varying t and finding the argmin. And if you let t approach 0, well, then 1 over 0 approaches infinity, and the barrier term becomes very important. So you get the analytic center. And as t goes to infinity, you get the LP optimum, right? And so the central path has at one end of it the analytic center, and at the other end the LP optimum. And in fact, the central path is smooth, infinitely differentiable at every point. As a matter of fact, I won't prove it, but the gradient of the central path is related to the Newton direction. It's just going to be H inverse C, right? So it'll be, times some constant. So it'll be proportional to that. C transpose, oh no, so at every finite t, you're still going to be pushed away from the boundary, right? This function is an actual infinity outside the feasible region. And so for no finite t do you ever get to leave the feasible region. And so as t goes to infinity, you actually, this gets less and less important. The forces get smaller and smaller, but they still shoot up to infinity very, very quickly as soon as you're going, along and along and along, and then you get close to it, and suddenly, wham, the force pushes you away from the feasible region, from the boundary of the feasible region, right? So that's a good question. It's basically what you're doing is sort of delaying the point at which this kicks in and overwhelms the optimization terms. Okay. So you can find a direction that goes along the central path. You can find the gradient of the central path with respect to t. And so it's a smooth curve that connects the LP optimum and the analytic center, right? And both the LP optimum and the analytic center are useful points, so maybe a path connecting the two of them is useful as well. We can always hope. The other thing is that the central path, I should mention, is also invariant affine transformations. Right, just like the analytic center was, and just like the LP optimum is. Okay. So just like we had for the analytic center, there's a force field interpretation of the central path. The only difference is that we have a force for trying to go in the direction of the objective vector, and the higher we put t, the longer the arrow is in the direction of that force, and so there'll be a different trade-off between the repulsive forces from the barrier and the optimality force from the objective. Okay? And just as before, the central path point is the equilibrium where the forces balance. So we can do Newton's method for the central path. It's going to look really, really familiar, right? So we already calculated the gradient of that term. That's going to be minus 1 over t times the sum of 1 over the slacks times the constraint normals. And then we just have a c from the gradient with respect to x, right? And then the same thing for the Hessian. We get the 1 over t sum of si to the minus 2 ai transpose, right? And so the Newton direction is going to be h inverse times the negative gradient, right? So it's going to be, I'm just going to multiply through by a t as we do this. So we have, we'll call this sum si to the minus 2 ai transpose, right? So there's a matrix times the Newton direction has to equal the negative of the gradient. Remember, I'm multiplying by 1 over t, so that's the sum of ai over si minus t times c, right? And so this thing here, that's the only difference from the Newton direction that we had for the analytic center, right? We have the same Hessian, and the gradient is perturbed by c, right? And so if t is small, let's say 0, we get the analytic center, and you would expect that the algorithm sort of runs almost the same for small t as it does for analytic centering. Okay? Yeah? So as long as you can find a barrier function for your convex constraints, you can define something that's like the analytic center for a linear program. So there is, in fact, a generalization. I was going to mention that later for semi-definite programs, second-order cone programs, quadratic programs. They all have barrier functions that you can use. The log barrier here has a few special properties that make the algorithm work well, and those special properties actually carry over with appropriate generalizations to SDPs, SOCPs, right? All of the standard optimization problems. Is there a question over here? I thought I saw a hand. No. Okay. So one thing that you should be asking right about now is what happens to Newton's method when you pick t equal 10 to the 12? Right? You suddenly put some really huge number on the right-hand side, and so you could imagine that you would get really, really huge directions unless you just absolutely happen to cancel out with this term, right? And so it's going to be much harder to find a good initial point for really large t than it is for general t, for small t or for analytic centering, right? So when t is big, convergence here can suffer. We'll talk about that more later, but it's still a pretty interesting definition to think of the central path, right? And the other thing is that this Newton's method is actually surprisingly robust. So here's a central path example. So here's our favorite feasible region, and I've plotted just a bunch of points along the central path. So we have the objective pushing that way. At the analytic center, the objective doesn't do anything. You sort of push closer and closer to the constraints. The objective is almost normal to one of the constraints, and so what happens is as you get closer and closer, it just sort of veers off, right? The force starts to cancel the normal component of the objective, and the objective becomes essentially parallel to it after you've canceled the whole normal force, right? And so you can imagine this being a whole lot more complicated in a big feasible region, right? You would wind up heading where you're sort of you're influenced by an average of a very large number of constraints when you're at the analytic center. As you get sort of towards one side of the feasible region, some group of constraints might become more prominent, and then as you start veering off, some other set of constraints will become more prominent until eventually the only ones that matter are the ones that are excuse me, are the ones that are active at the optimum. Right? So the other thing I wanted to mention with this example is that I tried t from 10 to the 6 to 10 to the minus 6 on this, and it took on the order of 15 or sometimes a lot fewer iterations to solve the centering problem, right? So for a huge range of t, it was sufficiently well conditioned that just with an essentially arbitrary initial point, I found the analytic center quite quickly, right? And so that's nice. It's very robust. What this plot actually shows, this point down here is t equals 1,000, right? Then the next point is 500, 250, and so on. This one is t equals 1, right? And this one is t equals 10 to the minus 6, right? So once you get basically sort of big relative changes start meaning less and less once you get to the ends of the path. Yeah. Right. Well, so you can get, we haven't talked about convergence yet. Because this thing converges very, very quickly, you can get a solution to machine precision with just this. But yes, if you're worried about something that's more than machine precision, right, or if you're worried about stopping early, there are rounding procedures for going from an interior point to a nearby vertex solution. Yeah, 15 Newton steps was enough to get any one of these central path points, right? So the conditioning, while it could be bad, this is a pretty, I mean, it's a small problem. It's a, relatively nice looking feasible region. And so this is just easy. And so it just knocks it out of the park. Okay. So have we discovered a new linear programming algorithm, right? We just set t equals 10 to the 12, find the corresponding point on the central path by Newton's method. It worked really well for this simple example, but in general, it has convergence problems, right? So, so let's talk about alternatives. What might we do instead? Well, I said that the analytic center is easy to find, right? So the conditioning sort of is good for the analytic center. That's not, you can find problems for which even the analytic center is hard, but you can put a bound even on how hard that can be. So let's just assume we can start by picking a t for which we can find the corresponding point on the path, right? Some moderate value of t. Let's say t equals 1. Okay, so now we find that point on the central path. The same Hessian that we calculated for Newton's method to find that point, that lets us calculate the gradient of the central path with respect to t. So we can take a step along that gradient, and hopefully we wind up pretty close to the central path. And because we've initialized really close to the central path, Newton's method, assuming we didn't stray too far, is going to pull us back to the central path quadratically fast, right? And we can just do it again. So this is called a path-following method. Actually, it's such a good idea that it has at least 3 names: homotopy, continuation, and path-following. The most plain English is path-following, so that's what I'll use. And so the idea is we can just try and pick up the central path at some easy point, and then try and follow the central path in the hard direction towards the linear programming optimum. Right, and in fact, that's going to turn into a real algorithm, and that is the basic outline of all interior point methods for solving optimization problems. Yeah. We could try and solve we could try and do a path following using gradient descent. So the nice thing about Newton is that you can find the central path very, very accurately, right? And there are going to be some benefits of that. I'll mention them in a little bit. And also that it lets you get the gradient of the central path, given the Hessian of the log barrier function. But yeah, I haven't seen a lot of people who tried to do a first-order barrier method, but I can't think of a reason why it would not work. Right. So the conditioning. You're right. So the conditioning is going to get worse and worse as you get closer and closer to the boundary. But you could get around that by rescaling, right? And also you could get around that by staying close to the central path, right? So it could be that the conditioning is the reason that people don't seem to do it very often. But I know of at least one gradient descent based method that uses Daikin ellipsoids in it. It's kind of an interesting problem. So if you're trying to optimize a function that you're only getting noisy samples of, so you get noisy samples of the linear function, right? So you don't even get the gradient, you just get noisy samples of the linear function. So then the big problem is the expense of getting samples, and so you can afford to do some computation. So if you find the Daikin ellipsoid at your current point, that lets you figure out what directions you have to be precise about getting the gradient in, and it helps you converge faster. It was the first algorithm that I know of that got an optimal rate for that situation, where you get noisy samples of a linear function over a convex feasible region. All right, so let's try and get a little bit more intuition for the central path and hopefully end up with an algorithm. So I wanted to mention, just like with the lasso, we have both a regularization form and a constraint form of the lasso to get the lasso solution path. Same thing is true here, right? So instead of putting C transpose X into the objective and scaling the relative importance of those terms, you could put C transpose X less than or equal to lambda as a constraint. And the tighter, the lower lambda is, the sort of more you're going to be pushing towards the boundary. And just like with lasso, there's going to be a one-to-one mapping between lambda and t, such that x of lambda and x of t are the same point, right? We don't know the mapping ahead of time, but there exists one. This form is not used so much because it's a little bit less convenient. We don't know what the feasible values of lambda are, right? So the minimal feasible value of lambda is going to be the optimal value of the program. And the maximal non-trivial value is going to be the value where you get the analytic center, right? Because there's no point in moving away from the analytic center. That's just going to be the minimum of this term, unless you have a constraint that pushes you away from it. Okay? So we have, right, so we have that. All right. We can also, maybe unsurprisingly, take the dual of the central path problem. If you've been paying attention, you're probably not going to be surprised that I'm trying to do that. But it leads to something interesting. So we have, I'm going to write it out that ax plus b is equal to s, and s is bigger than or equal to 0. And so the penalty is the sum of the negative logs of s, right? So if we add a Lagrange multiplier y for this constraint, we get y transpose times s minus ax minus b, right? And we add that to the objective. And we can then carry out the minimization with respect to x and s, and that gets us the dual. So if we take the gradient with respect to x, right, we'll get c from this term that has no x's in it, and we'll get minus a transpose y. And if we take the gradient with respect to s, we'll get here a minus 1 over ts, right, plus y from this term here, right? And so what that means is that at the optimum over x, we're going to have c equals a transpose y, and s is equal to 1 over t times y, right? And so if we just substitute these back in, we will get that a transpose y plus a transpose y minus c is equal to 0, right? So those terms drop out. S is 1 over t y, so y transpose s is then just m over t, right? So that's this term. We're going to wind up maximizing minus y transpose b, right? So we're going to max over y. That gets this term. The only term left is this one, right? And so minus log s is log ty. So this is going to be plus 1 over t sum of the log of ty, t times yi, which is log yi plus log t, right? And so this I can then write as max over y, m over t plus m log t over t minus y transpose b plus 1 over t sum of the log of yi, right? So, and then that's going to be subject to the constraint that a transpose y is equal to c. Okay? And implicitly, y is greater than or equal to 0 because of this log here. Okay? So, here, these constants, they don't matter to the optimum, so typically people drop them, but it's good to know what they are, right? And so we now have something that looks like, I want to call it a standard form analytic center or central path problem, right? So we have the same centering constraint, but here it's for the variable itself rather than the slack. And then we have equality rather than inequality constraints and a positive variable. So it's like a standard form linear program, but with a log barrier, right? And we can, just as before, adjust the relative strength of the barrier term and the optimality term. So why is this interesting? Well, one thing is that it's very easy to find a point that's strictly feasible for the inequality constraints, right? So you just have y equals 1, right? Every component of y. So yi equals 1 for all I. So that means that I can use now an infeasible start Newton's method, right? I start with that y, which doesn't satisfy the equality constraints, but we know how to make Newton's method try and satisfy equality constraints over time. And so I can just run this from a trivial initializer, right? So that means that I no longer have to worry about finding a feasible point to start, right? So that's kind of cool. The other thing is that this gives you a very slightly different Newton update. If you write it out, I'm not going to write it out because it's very similar to the one that we found before. It's not exactly the same, but you can see that it bears a striking resemblance. So it's just a slightly different algorithm, which has very similar behavior and guarantees. Okay? So, so any questions about the dual of the central path problem? Okay. So the other thing that's cool about the dual is that there's this really nice correspondence between the prime and dual central paths, right? So it's not just that the dual of a central path problem is another central path problem. In fact, there's a very strong correspondence between every point on the central path and the primal problem and a corresponding point on the dual path, the dual central path. So here's just the primal and dual central path problems copied from the previous slide and the Lagrangian. If we take the gradient with respect to s, right, we had that before. It's just y minus 1 over ts, right? And so that just means that si times yi is equal to t, or in vector notation, Hadamard product between s and y is t times the all ones vector. Right? Sorry, not t, but 1 over t, and then the same thing here, all ones vector divided by t. So that means that, whoa, and the other thing is that once we run the Newton's method, right, if we do an infeasible start Newton's method here, we'll actually get the value of the Lagrange multiplier for this constraint out of that infeasible start Newton's method, right? So we'll have that x. And we can also get the x, right? We know that ax plus b is equal to s, and so we know that we can get y from we can get s from y, and then we can do least squares to solve for a, right? So from multiple different roots, we can get x just by ax plus b equals 1 over ty, right? So that's the multiple roots to get a dual, to get a primal feasible point, primal central path point from the dual central path point once we've satisfied the KKT conditions. Okay? So, so that's nice, right? To every point on the primal path corresponds a point on the dual path. Even better, it turns out that we know exactly what the duality gap is going to be between these 2 points, right? So at the optimum, one of the KKT conditions is that the primal value has to equal the dual value, right? So the primal value was C transpose X minus 1 over T sum of the log slacks. The dual value was this constant plus 1 over T sum of the log variables minus the linear part of the objective. And so from this, right, we know that sum of log SI yi is equal to, well, SI yi is just, whoops, not T, but 1 over T, is just sum of minus log T, right? And there are this here, right, because of the product, this is sum of log SI plus log yi, right? And this here is just equal to minus m log t, okay? And so here, what we have is, if we move the log s over here to this side, right, what we'll get is 1 over t times minus m log t, right? And so we can just get rid of that term, and that term all at once, right? Everything just cancels. Beautiful. And so we just write this whole thing out as C transpose X plus Y transpose B is equal to M over T, right? So the duality gap is just M over T. So there's this beautiful correspondence between the primal and the dual central paths in that from a point on the primal path you can get a point on the dual path and vice versa, and those points have a known duality gap that depends on the t that you chose, right? And so we know exactly what the gap is, and that means since we have a bound on the gap, we also have a bound on the suboptimality of either of those points, right? The primal and the dual points can be suboptimal by at most m over t. And so it's not just that we can approach the optimum by varying t, we know exactly the rate at which we approach the optimum, right? We know that the duality gap will be m over t if we pick t as the parameter. So I think that's probably a good place to stop, and we'll pick up with this again at the beginning of class on Tuesday.